Today we're going to do separation of variables again.
Damn, this is good because I don't know how to do this.
Well, it's just sort of a tangential thing. We're going to do it for what we call PDEs, and the main topic of this is the heat equation.
Does everyone know why no one shows up?
Okay, so yeah, I don't really like throwing formulas at you cold turkey, so I'm going to try to sort of explain where things are coming from just a little bit, not too in depth. But we'll try to get through that quickly so we can finish this. This is the last topic we will need to cover. Basically, our goal in this section it's an application of PDEs and where do you see this? Sort of wanted to leave that as a surprise, but what did I say? To find the function. That describes the heat distribution in an insulated bar. The bar with, we'll call it length L. Okay, so that's the goal. We're going to try to figure out how to.
Oh, 207 physics.
Yeah, sort of. Well, you don't really do the PDEs in that thing. Well, okay, so basically the idea is we have this bar. Right? So we're measuring it along, let's say, the x-axis, where this endpoint is x equals 0, this endpoint is x equals L, and basically what I want is, I need a function, let's call it u of xt, that gives me the temperature at position x at time t, right? This is sort of where we're going. And of course, once you know how to do it for a bar, you can apply it to other surfaces, but for 391, we talk about doing it for a bar. So there's something of length L. We say it's insulated. The bar is insulated. i.e., the temperature at the endpoints is 0. i.e., u of 0t equals u of LT equals 0. Right? So pretend that we have insulation on these guys, so there's no temperature, there's no heat coming in or out from the ends, but along the bar we have heat, and we want to sort of measure how much heat we have. And also suppose the initial temperature distribution is known. Given by u of x 0, right? When time is 0, let's say it's given by some function f of x, which means f of x will tell me what the temperature is for some position x along the bar at the initial time, right? So that's sort of the setup. And this is, of course, t is time here, so this is for all t greater than 0. Right? We're going to sort of measure this. So I'm going to cut to the chase. They actually derive this in the appendix. It's a really long derivation. I'm not going to really derive it. I'm just going to tell you what it is, and then we're going to talk about it.
Just don't care about it.
heat conduction equation. People usually leave out the word conduction. It has the form following: alpha squared uxx plus equals ut. And they derived why this is the equation that governs it in the appendix. You can read it if you're interested. Notice here I'm taking partial derivatives. It's actually a partial differential equation, just a differential equation where your derivatives are partial derivatives, not ordinary derivatives. And basically that's because our function is a multivariable function here, right? So the derivative we're talking about are partial derivatives, right? This will be the equation that governs them. This is called the heat equation, okay? So this is valid for x0 to L and t greater than 0. And we're going to talk about how to solve this. Alpha squared is a constant. Called the thermal diffusivity constant. It is determined by the material. Different materials will have a different alpha squared. You don't have to figure this out. It's determined by, we'll give you alpha squared whenever it's necessary. It is determined by the material. So it's based on the physical properties of the material. In fact, alpha squared is equal to kappa over rho s, where kappa is equal to, what do we call it, the thermal conductivity. It's a measure of how fast it conducts heat. S is the specific heat of the material. Which you learn about in chemistry. Rho is just the density of the material. Don't worry too much about this. We'll give you what that constant is whenever it's necessary. We'll tell you alpha squared is 1 or all we'll do is we'll give you the equation, and of course if you know the form of the equation, you'll know the alpha squared is just the coefficient of uxx. So in any case, you'll be given alpha squared. You don't have to worry about figuring it out. So we have an eraser. So now we're going to talk about how the problems in this section are usually presented. It's called a boundary value problem. And it's the problem that we're going to want to solve here, right? So you'll be given three things. You'll be given alpha squared uxx equals t. You'll also be told whether it's insulated or not, so they'll tell you that u of 0t is equal to u of lt equals 0. This is called the boundary conditions. I'll abbreviate by BC from now on. And they will tell you the initial temperature distribution. So the temperature at 0 is given by f of x. This is given for all t greater than 0. It's called the boundary condition. This is given for all x along the bar. This is called the initial condition. Which I will abbreviate IC from now on. So they'll pretty much give you these three things. So they'll say, okay, the heat conduction equation for this certain material is blah. The endpoints are insulated. and this is the function that gives you the temperature distribution at the initial state, right? And they'll want you to find u of xt, which is a function that gives you the temperature distribution at any state, right? Any state for t greater than or equal to 0. Okay. So now we are going to, we want to solve this. We're going to talk about what the solution looks like, and then we're going to actually do some examples of finding the solution. Now the thing is, the fact that this is a multivariable equation sort of makes things difficult. It's sort of hard to predict what the derivatives would look like. So we sort of launch a prayer and hope.
So Jhevon, here you say that u is a function of length and time.
Yes.
So the 0 represents the length.
I'm saying it's x and t. This is position, this is time. Or they'll give you. So x is representing the length. Well, what point along the length of the bar you're at, t represents. They might switch these on you, but just know that x would represent the length along the bar, t is time. So, yeah, we assume that our lives can be made really easy and say that u of xt is just a product of two functions, one of which is purely a function of x and the other which is purely a function of t. Why? Because it makes our life easier, and we have things like the existence and uniqueness theorem. So we know if we find a solution at this point, we're good. Let's not worry about it. And it turns out by making this assumption, we can actually find a solution of this form, and it has some nice connections to what we've done before. So in previous semesters, they usually ask you to do separation of variables, but I don't think it's on the final this semester. So we made this assumption, we use separation of variables. So if that's your u, it means that uxx would just be x double prime t, right? Because t is a constant, I would just differentiate this twice. And u of t would be xt prime, right? This means we just plug these guys into that. So we have alpha squared times x t equals ut, which is x t prime. This means that I get x double prime over x is equal to 1 over alpha squared times t prime over t. Separate the variables. Now here we make an important observation. This guy, x double prime over x equals 1 over alpha squared t prime over t, must be equal to some constant. The reason being, these are two different variables. They're varying at different rates. The only way we can ensure that this equation holds in all cases is if these two expressions are constant. They're actually not changing with respect to each other, right? Because we don't want the x to be doing whatever it's doing while the t is not false. Yes? What? I'm just sort of deriving the solution. You don't really need to know this. Just, if you're interested, you just watch it in slow motion.
This guy.
Right? Okay, so we get this guy, and basically 10.5 goes to this. You can even read it yourself. Actually, I would recommend that you read 10.1, which we're going to use some of that, and 10.5. But I just want to really get to the crux of the problem, so I'm just going really fast through this where it all comes from. Right? So if we assume that these are constant, then we would end up with two equations, x double prime plus lambda x equals 0, and t prime t equals 0. So basically what we have is we're given this differential equation, we want to be able to solve it, so we make it this assumption that we can write our function this way. We take our partial derivatives and we plug it into the differential equation. We get to a point where we assume it's constant because it's the only way we can guarantee that this equation will hold at all values of t and all values of x. And then we can therefore separate them. We can set this equal to a constant and this equal to a constant, and we end up with two separate differential equations. And this process is called using separation of variables to transform a PDE into two ODEs. In previous finals, you'll see them having questions like that. I don't think it's on this year's final.
That means it's
So this means by trying to solve this problem, we get to a system of differential equations, and 10.1 actually deals with how to solve these equations. So I'm just going to tell you what they are. They're actually not. It's just a second order differential equation. You can find that. And this is a first order differential equation. All right, so this one is actually separable. And that one you can use, x equals e to the rt. Right? It turns out that the only solution that makes sense in this case is going to be the complex solution. It's going to be the only one that will work out. Right? You're basically going to get something with cosines and sines, but it turns out that when you go through the derivation, and again, you can read through 10.1 to see it, or you can work through it yourself and see why. The coefficient of cosine is going to be 0, only the sine is going to be left over. The coefficient of that is going to be arbitrary, which we're going to sort of match up with this to figure out what the coefficient is to be, etc. Right? So, So when you go through 10.1, or you can try it yourself, you'll find that solutions are given by the following. That is actually going to be your x. You're going to realize at some point you had to set the sine equal to 0 to deal with this initial condition here. And what's going to happen is you're going to find that sine is 0 an infinite number of times, right? At every n pi, in fact. But because we're breaking up the period into 0 to L, we divide by the L. If you go through the calculations, you'll see it. So we end up with a solution for every n. We get a different sine function that will solve it, right? You can also find, and if you need help figuring it out, 10.1 can help you out again. It's not that complicated if you actually try it. You'll find that your lambda for each n will be given by this guy. This is over L. And again for n goes 1, 2, 3.
There's always going to be an odd Fourier series, right?
I don't know, maybe. Okay. These guys are called Eigen. I don't know if I should even tell you the names. You're not going to really know what these are.
You spelled it wrong too, right?
What? No, I didn't spell it. Eigen Values. These guys are called Eigen Values. The solutions are called Eigen Functions. But when you do linear algebra, you'll understand more what those mean. Let's actually go. So if you plug this guy into here, we will get that t is actually equal to a constant times e to the minus n squared, pi squared, alpha squared, t over L squared. So I know they look complicated, but it's not. If you actually work through these, they're actually pretty simple differential equations to solve. They're just constant coefficients, right? You work through it, you'll see that you'll get these. I just want to skip, don't want to lose the time deriving everything directly. Right? So that will be our x, that will be our t, which means if I assume u is just the product of these two, I can figure out what the u's look like. So I'm just going to multiply these. E to the minus n squared I squared alpha squared t over L squared times sine n pi x over L. Because I assume they were the product. You split them up into these two ordinary differential equations, you'll find that those are the only solutions that make sense for us. And then we just multiply them. Right? So since linear combination of solutions is a solution, we get that our general solution we can sort of write as a linear combination of all guys like this. But how many guys like this do we have? An infinite amount, right? Starts from n, counting from 1 up to infinity. So a linear combination here will actually be an infinite series. So it means that we'll have to, it has to be the case that our u of xt looks like that if we do this assumption. But we have a condition to fulfill that u of x0 is actually equal to a function f of x, right? So this means if I go here and I plug in t equals 0, I should obtain a function f of x, which means that u of x0 is equal to f of x, which is going to be equal to, if I here I go and I plug in t equals 0, then I get e to the 0, this is just 1, and I'm left over with cn sine n pi x over L. And what is this guy? Gasp, right? It's the Fourier series, right? So this is, it turns out that the solution to the initial condition for this system of equations is actually a Fourier sine series. This means the Cn, these coefficients here that we have to determine, are the Fourier sine series coefficients. Therefore, finally, why I said all this is the punchline. The solution to alpha squared uxx plus ut u of 0t equals u of lt equals 0. It's the boundary condition. T greater than 0. It's the boundary condition. And u of x0 equals f of x, for x between 0 and L. It's the initial condition. The solution to this system, this boundary value problem, is given by u of xt equals the series n goes from 1 to infinity of cn e to the minus n squared pi squared alpha squared t over L squared sine n pi x over L, where the Cn is equal to, what's the Cn? Where's the n? The coefficients of the Fourier sine series, what do they look like? 2 over L, that's right, 0 to L
f of x.
of f of x times sine n pi x over L dx. And this is the whole point. That's the important part. Actually, I could have just told you that, but I didn't just want to just tell you that. Okay. So you won't have to derive it at any point. So that's why I wasn't really worried about going very slow through this derivation. At some point, you might have to derive it. I've seen students come who are doing masters in civil engineering, and they came to the tutoring center, and it turns out that a lot of their problems, they had to like derive these things. So at some point, you might have to do it for some of your engineering classes. I'm not sure if you'll do it in undergrad classes, but at some point, if you go far enough in engineering, they'll expect you to be able to derive this on an exam and things like that. So it might be to your benefit to actually read through 10.1 and 10.5 and try to get through it slowly yourself, because the day might come when you'll actually need it.
Just for that one exam. Just for that one exam.
I got it.
But it's not just for that one. But for, as far as we're concerned, this is all you need to know, really. Right? If I give you a problem that looks like this, the answer looks like that. That's the answer, right? And I'd expect you to be able to find the Cn. Of course, the L is going to be given, and the f of x is going to be given, right? And then you'll have to go through this, right? That's sort of the summary. Okay, so let's do a few examples. So let's say this is a question. One thing you should appreciate is that this could actually be a question in its own right without using something that we've done before. They can just tell you something like, okay, there's a bar of length 1 whose alpha squared constant, whose thermal diffusivity constant is 2, right? And we want to find, and if we know that the initial distribution of temperature is 2 degrees Fahrenheit throughout the bar in the initial state, how is the heat diffusion going to run throughout the bar as time goes on, right? If you know the ends are insulated, what's going to be the solution, right? And it turns out you'll have to go through and find the Fourier sine series coefficient to actually solve it, but we actually did this last time, because we'll see here that our f of x is actually just 2, which we've actually found before. Here, our Cn was, what was the answer we got to that? We actually did, it was 2 over 1 times the integral from 0 to 1 of f of x, which is 2 sine n pi x over L, which is 1. Right? And what was the answer that we got here?
Negative 4 over n pi.
It was 4 over n pi, or was it 8 over n pi or something?
Whatever was finite.
is 8.
What was it?
Negative 8 over n1.
-8.
No, it was 8 over n cubed by cubed sine n pi x.
No, just the coefficient, right? Not the whole solution. Just the Cn. It would be our Bn in the last example. From Bn it was what? We got like 0 for like even stuff, and then we got something else for odd things.
I think it was, wait, no.
8 over n cubed pi cubed. That was the full thing?
Yeah.
It was for odd n, right?
Yeah.
Okay. So, this means, right? So if you didn't do that before like we did, you'd have to actually do that. Right? So you'll see here that your u of xt is just your f of x, right? And all you're going to do is you're going to plug it into this formula and find the coefficients, which we did last time. It turns out that this would be the answer. And so your solution would look like what? Well, you're going to take this guy, plug into that formula. I'm going to do one from scratch eventually, but I'm just piggybacking off work that we've already done. You're going to take this guy, plug in this formula, plug in your alpha and your L, and that would be your answer. So you'll have U is the sum, it only works for odd n, of Cn, which is going to be this, 8 over n cubed pi cubed times e to the minus n squared pi squared. Alpha squared is actually 2. T over L, which is 1. And so it's sine of n pi x over L. Yes.
So alpha is 2.
Yes. You can see it. Remember the form is alpha squared uxx equals u.
3 squared.
What? No, the original form has alpha squared in it.
Oh,
Right? Look, from the general form, whatever is the coefficient of uxx is going to be alpha squared. So alpha squared happens to be 2. The alpha is radical 2, but we don't care. Alpha squared is what shows up in the formula. Whatever number is here, we put it in. Okay. Let's look at another example. Again, one that we did some of the work for, but I'll write out what the full problem looks like so we can actually see it. This is from fall 2011, problem 10. So here's how you're typically asked about this problem. They usually don't actually talk about an insulation bar, but an insulated bar, but that's sort of what's going on. You know it's an insulated bar. Okay, so compute the sine series for function f of x equals x times 1 minus x on the interval 0, 1. And then it says part B, use your answer A to obtain a series solution and they sort of switch the x and t on you, but it's t is still time and x is still position. for the PDE with x in this interval greater than 0. And then they said here ut is equal to 9uxx u of t0 equals u of t1 equals 0, t greater than 0. And we have u of 0x is equal to x times 1 minus x for x between 0 and 1. So this is a final question. This is like typically how they'll ask you the question, right? So in part A, they'll just say, find the Fourier sine series for this function, right? Then in part B, they're like, use your answer from part A to solve this equation, right? Which is sort of why I sort of did the example like that. Okay, so how do we do it?
I think we already found the Cn for part A from last part.
So remember, note, the solution is given by u of xt equals the sum from 1 to infinity Cn e to the minus n squared pi squared alpha squared t over L squared sine n pi x over L, where the Cn is just 2 over L, 0 to L, f of x sine n pi x over L. And what is L equal to here? 1. It's still all going to be the number here, right? It's between 0 and 1. So we know that our L is equal to 1, right? Because it's always from x goes from 0 to L. And our f of x is, and I told you right here, x times 1 minus x. And this means, now we're going to find the Cn, right? It's going to be 2 over 1 times the integral from 0 to 1 of this function, x times 1 minus x sine n pi x dx. And yes, we actually did this last time. We did tabular integration on this. We multiplied this in, make this x and minus x squared. We did the integration. And what was our final answer there?
Actually, that one.
Yeah, that was the correct one.
What?
A over n cube pi cube is the correct one.
That one is
For
wrong.
this function.
Because you use
That solution is for this one.
So
why did you guys tell
me this for this?
So that's wrong, what you said.
The answer for that one is A over n pi.
Yeah, 8 over n pi.
This was just n pi?
Yeah.
And that one is actually 8 over n pi cubed?
Yeah. 8 over n pi.
It's too early in the morning to read, right?
Well, you're the teacher, you should be able to catch that.
You have the notes in front of you.
Yeah, but you didn't catch it like, oh, this looks not right.
Just continue.
Let's move on. Okay, so this was actually 8 over n cubed pi cubed. And this was again for n odd, I suppose.
Oh, no.
Yeah.
Yes, right? It was 0 when n was even, and it was that when n was odd. And so what's our solution now? U of xt is, let's go back here. So it's the sum for overall odd integers of this guy, 8 over n cubed pi cubed e to the, our alpha squared is what in this case?
9.
It's 9, right? Just from this, it's whatever the coefficient of uxx is. So I'm going to have minus 9 n squared pi squared t over L squared, which is 1, so that's just the self, and sine n pi x over L, which is just 1. Huh?
So the solution to part A is the Cn?
Yeah. 4 easy.
Yes, this was the solution to part A. And in part B, you pretty much just write it down. There's actually nothing left to do. I believe you're asking if I give you this formula. No, you have to actually memorize this. Like what I put in the box last time, that was right here. We're given this sort of equation, this is the solution, you have to actually memorize that. They're not going to tell you that. The only thing they'll give you is the table of Laplace transforms. They're not going to give you anything else. So this is actually something you have to memorize. Or you could derive it and take like half an hour in the final. It's up to you, whichever you like. Right, so yeah, this form, you just have to know this, right? Know that the solution looks like this, the Cn is given by this. Just go through it. Okay, so those two actually use things that we've done in previous classes. Let's actually do a problem cold turkey, like from scratch. Another final problem very similar to this one. Let's do the whole thing. So this is spring 2011, problem 10. A. Part A said compute the sine series for, going easy on us, f of x equals 1 on the interval 0 to pi. What? No. And then part B, it says pretty much exactly the same wording, they just changed the function. Use your answer in part A to find the solution to, I'm not gonna, they phrase it similar to that, but they basically said this was the situation. U of t is equal to 64 uxx. U of t0 equals u of t pi equals 0. Greater than 0. This was the boundary condition. And they said that u of 0x is equal to just the function 1, where x goes from 0 to pi. Now, they actually let's do part A. How do we find part A?
BNs.
We need to find the bn's. So bn would be equal to what? 2 over L, 0 to L, f of x sine n pi x over L dx. Here, okay, what's our L here? Pi, because it's always from 0 to L. So this is just 2 over pi times the integral from 0 to pi of our f of x is just the function 1, right? Sine, and here our L is pi, so it says pi over pi, they cancel. So it's just sine of nx. So this is 2 over pi times, what's the integral of sine nx?
No, 1 over n.
1 over n.
So sorry.
Yeah, negative cosine.
It's negative. Negative 1 over n cosine this between 0 and pi. So this means that we have 2 over pi of, plug in pi here, I get minus 1 over n cosine n pi, plus, if I plug in 0, I get 1 over n. Right, because cosine of 0 is 1. Now what does cosine n pi look like? Again, it splits into two things. So it's 2 over pi times, well, if your n is even, like cosine of 2 pi, 4 pi, 6 pi, 8 pi, etc., this gives you 1, right? Which means that this gives you nothing, right? 0. This happens for n even. Now if I plug in odd n, like 1, 3, 5, 7, etc., this will give you negative 1, times this negative makes it positive 1, plus that you get 2 over n, so times this, so it's 2 over pi times 2 over n equals 4 over n pi when n is odd. And that will be your answer to part A.
Equal to 0 when it's even. When it's 2 times 0, no, it's 1.
Can we get?
Oh, yeah,
Yeah, I'm looking at the cosine n pi, right? It actually,
I got it now.
for even n, it always gives you positive 1 as the value. And for odd n, it always gives you negative 1 as the value. So if it's even, we end up with 0. If it's odd, we end up with this.
But with these type of problems, you expect me to write
Yes.
in this one.
If you're in any other class, you probably get away with the other thing, but in my class, you have to do that.
Don't do that.
Aren't you glad you're in my class?
No.
So glad. Okay, so that was actually part A, right? You just do this integral. You have to know the formula to find the Fourier sine series coefficient. Again, this is not going to be given. You have to just remember this, right? And so, oh, they actually said compute the sine series, not just the coefficient. So the whole series would be, this means f of x is equal to, what would this look like in the Fourier series?
Series from 1
Remember your a0 is 0, all your a's are 0, so this is just the summation.
to
N goes from 1, well, it's only odd n, so I'll put n odd of the coefficient here, 4 over n pi of sine n pi x over L, but my L is pi, so just, that's the whole answer, right? That would be the Fourier series for f of x, the odd Fourier series, right? So that would actually look like the function 1 on 0 to pi, and then it will be negative 1 from 0 to minus pi, and then this repeats. And your Fourier series would look like. That's sort of what it would look like. Okay, so that was part A. Now part B. So part B says use your answer in part A to find the solution to this problem, right? So we know the solution looks like what does the solution look like?
sum from 1 to Cn. E to the negative n squared pi squared.
N squared pi squared alpha squared t over L squared times sine n pi x over L, where the Cn is actually going to be 2 over L integral from 0 to L of f of x sine n pi x over L dx. Now notice that our L and everything is all the same, so we'll actually get, in part A, we're going to use the answer. That's why they say to use the answer to part A.
Because I think we need to write down 2n minus 1 instead of n, because the n over here is different from the n over there.
Going up? No, I'm summing over odd n. So it applies to everyone in the series.
I know what part A, that one's fine, but when plugging to part B, we need to use 2n minus 1 instead of n out, right? Because the n there,
I could, but I could also do this.
but the n, the e to the something n, that one is different. Oh, still square.
No, it'll still work out the same. Yeah. This, I mean, I don't mind either way. This is actually equivalent to just saying something like n goes from 1 to infinity of 4 over 2n minus 1 pi times sine of 2n minus 1 x. That's equivalent. And I don't particularly care that you write it like that. Though.
Yeah, part A is equivalent, but when you plug into part B, it's different. The n is different. The
No,
n-
when you plug into part B, you reinterpret the problem. Now this problem doesn't stand alone, it's actually within the context of that. Right? The n here will be the same as the n's over there.
No, but the n, the e to the something n, that n is different.
No? All the n's are the same. So this we actually found, this was, what was it, 4 over n pi? So this is 4 over n pi when n odd, 0 otherwise. So this means u of xt equals, I can just say it's odd n because my Cn is going to give me 0 whenever it's even, so I can just write n odd of 4 over n pi e to the, what's going to be the power here? Minus 64 n squared pi squared t over pi squared, right? Because L is pi, so the pi squares will actually cancel. And so we end up with this. Sine of, again, L is pi, so this just is nx. And that will be your solution.
Professor, but if we use that one, use the 2n minus 1, we will still use e to the negative 64 n squared times t, so it will be different. But the sine is 2n minus 1. You know what I mean? The n
No,
is
they'd all be the same.
Show her what you did.
Right, you could have written this as n goes from 1 to infinity of 4 over 2n minus 1 pi e to the minus 64 n 2n minus 1
No, it's n squared, right?
t sine of 2n minus 1 x.
So the n, the e to the something n, you don't actually mean is to the n, it's whatever the coefficient is. Because you,
It's a series, right? It's like I'm adding something, then plus 0, then add something, then plus 0, then add something, then plus 0. If you ignore the plus zeros, there's no difference. I can actually skip some n, I don't care. Right? Because for certain n, this coefficient is 0. It kills the whole term. Why do I need to keep it around? You know what I mean? So I can actually ignore some terms because this coefficient will give me 0 for some particular n's whenever your n is even. So I really don't care about the even n anyway. As far as the series is concerned, it'll give me the same thing. And even if here I put just n goes from 1 to infinity, what's going to happen is for even n, it's actually going to be 0. So it actually doesn't make any difference either way. This is just to emphasize that we know it'll only work for odd integers, right? Sometimes it only works for one set of integers, not others. So in any case, it doesn't matter which one you write. And even if you write 1 to infinity, it actually won't matter either. Because when your n becomes even, this guy here is going to give you 0. So that term is going to die. And then only the odd ones will appear. Now, I believe the solutions for this one is actually up online, and for part B, they took like a whole page because they actually derived, they did the separation of variables and all that. I don't care if you do that. You just tell me that this is the solution and be able to plug it in, and I'm.
What?
So
Nothing? Yeah, yeah.
for this one, the period is gonna be 1, right?
Thanks.
Or that's just the length. You
The,
said L equal 1.
for, well, L equals 1 was for the previous problem.
Oh. Now make this one.
Our problem actually starts here.
I know, but
So technically here, if you look at it as a Fourier series, the period is actually 2 pi. Remember, the period is always 2L, the way we set it up. Here, L is pi. So the period, as far as this guy is concerned, the period is 2 pi, right? It goes between minus pi and pi, and sort of look like a backwards Nazi sign. But
it's the length of 2, basically, right?
yeah. But for your heat equation, you don't really think of it in those terms. You just plug it in. This is the series solution that will solve this partial differential equation. So that's normally the format in which it's given in a final. In your homework, they might just give you this part. And they just say, oh, there's a rod of length pi, and we know that this is alpha squared. Find the heat diffusion at any given time and position, and then you'd actually go through the same thing, right? Except in the final, they usually ask you to do this part first, and then they ask you to do that part second, but you don't have to think of it that way. It could all be one fluid problem. No pun intended. That's sort of it. So we're done. I'm so excited. Yes.
No, you're not done.
Can you also get a function that's even? So you have to find out that.
It's possible, yeah. When you get to this point, you'll worry about that. Right? Over here. When you're finding the Bn, it just might be the case that it will work for even ones, it'll give you something, and for odd ones, it won't. So it depends on your answer to part A. It might also work for everyone. In this particular case, it only worked for.
But for even functions, you need to find out the A as well.
Well, they specifically ask you for the sine series here, so you only need the odd ones.
Would they let you know? Like,
Yes.
would they ask you for Fourier series instead of sine or cosine? And then you have to figure out which one it is.
Hey, shh, quiet. Would part A actually for a Fourier series? It's possible, statistically not very likely, but it's possible. If they did just actually compute the Fourier series for this, then you would know I'd ignored what I computed for the ANs and only use the BN in the answer to part B.
Okay.
So, but they usually they'll be nice and just let you do the sine and try to not confuse. Okay, so that is the end of 391. Very, what?
Professor, but it
Not the
tells-
end yet. We
It
have another
tells you
question.
it tells you to find the Fourier series and doesn't tell you if you need to find the odd or even one. How do you know if you're odd or even one?
Side.
They said the sine series.
No, I mean they only tells you to find the Fourier series for fx equal to 1 on interval from 0 to pi.
Well, this wouldn't be enough information actually to find a Fourier series in general. It has to be on a balanced interval to know about a Fourier series. So if they tell you this, they'd have to say extend it as an even or an odd function, or otherwise they'd actually tell you what it looks like on minus pi to pi.
Okay.
And then you have to figure out how to deal with it. Yeah, so are there any other questions?
When's the exam?
I didn't post it. So the next test is on Wednesday.
Wednesday?
And the final is on Monday.
Monday. And when is the Monday?
Huh? No, I'll send you the seating assignments and everything.
And what time is it?
It's in the I think it's in the Arno Theater. It's on the first floor here.
I know what you're talking about. So what's
It's like at 1 p.m. or something like that. I'll send you guys more information. It's actually in the syllabus. Yes.
Wait, 1 p.m.?
What?
Next Friday is final.
Yeah, I'm pretty sure. Yeah. The 18th. The 18th is our final. Yeah.
1 to 12. Okay, after that. No, because like 1
to 3:15. It's a 2-hour 15.
No, because like my first exam was at 10, so I can finish that and then come here.
Anyway, I have stuff for you guys to do.
Oh, fill out like.
You get to tell the world how much.
Give them all
how
like
much you love
zeros
me.
and ones, you know.
I need a student volunteer because I can't help it either.
When we get to Wednesday? How long is the final?
Yeah. It's 2 hours and 15 minutes. It's usually
When are you gonna get the exam back?
Wednesday, you think?
Okay, well, are you planning to keep our 45?
I can keep a review session, but it would have to be like the weekend, so Friday, Saturday, Sunday. I don't know how many people can make it. I'll probably film it as well. And we'll work on that. But yes, now to tell everyone how you feel about me in this course.
Boo.
Nothing but love and adoration and
You're
affection.
right.
Right? Or else. I'm kidding.
You said it on camera, bro.
No, I'm joking. They don't allow me to see the results till like a